Let's think about what happens when we actually have an algebraic expression for a function. And in order to start to talk about this, let's take a look at just a relatively ordinary function. Consider the function capital F of x equals the absolute value of x plus 2. Now I just named a function with a capital letter, so you should suspect that something a little bit fishy is going on. Usually I'll name functions with lowercase letters. And in fact, something slightly fishy is going on here. Because notice that this function actually does two things. Whatever the input it has, it does two things to that input. Whatever input I give it, first this function adds 2, and then second, whatever the result is, this function takes the absolute value. And of course, this is true of almost every function that we write an equation for. It's going to do 2 things, 4 things, 5 things. Most functions take a lot of steps to evaluate. When we see a function like this, we can imagine it as being made up of smaller functions. So this function, for example, if we say, okay, well, let g of x be the function that just adds 2, and h of x be the function that just takes the absolute value, then our function f, let's see, we do g first and then h. So our function f is just h composed with g. Practically any function that we like, if it has more than one step to evaluate, if it has more than one operation, we can break it down in this way. When we look at taking the expression for a function that we get from composition, we just proceed in the opposite direction. If I want to say, what is h composed with g of x, I want to find the function that first does g, and then does h to the result. So I could say, there are actually 2 ways I could go at this. I could think about the g part first, or I could think about the h part first. I'm going to attack this by thinking about the g part first. H of g of x, well, that's just h applied to g of x is x plus 2. And then what does h do to that? It takes the absolute value. I could also approach this by resolving the h first. H of g of x, well, h takes the absolute value. So h of g of x is just the absolute value of g of x. So it's the absolute value of x plus 2, since that's what g does. Either way, of course, we get the same answer. You can approach this either way. And that's going to be our general approach to taking a composite function, even if the functions that we're composing are themselves interesting functions that do more than one thing. So suppose f is the function that multiplies by 2 and then subtracts 3. So f of x is 2x minus 3. G is the function that multiplies by 5 and then adds 2. So g of x is 5x plus 2. Then if I want to take f composed with g of x, well, that's f of g of x. So that's f of 5x plus 2. What does f do? It takes its input and multiplies it by 2, and then subtracts 3. In this case, its input is 5x plus 2. Now that's it. I'm actually done. Right, f composed with g of x is 2 times 5x plus 2 minus 3. But if I'm keen to do anything more with that, I probably want to simplify. Right, so we'll distribute, and then we'll combine like terms. And there we are. We have a nicer expression for f composed with g. I'm going to give you one of these to try as well. Let h of x be 3x plus 1. K of x be just the function x squared. Find h composed with k of x. Pause the video and try this now. Okay, h composed with k of x, that's h of k of x. K of x is just x squared. So we want to take h of x squared. H of x, that's just the function that takes its input, multiplies it by 3 and adds 1. In this case, its input is x squared. And there really isn't anything we can do to simplify that, right? We're just left with h composed with k of x is 3x squared plus 1. And that's all there is to it.